We didn't.
Oh, God.
Why'd you set him up for that?
That was the one thing I heard.
Yeah. All right, let's do another related rates problem. That's just what we're gonna do. Every day we'll just go through another, this is a process, you just gotta get good at it. So put all your stupid phones away and, you know, quit worrying, just don't worry about FOMO,
Oh.
you're not gonna miss out on any, they're just missing out by not being here. Anybody you'd ever be communicating with is really the one missing out. So solving related rates questions, 4 simple steps, right? This really helps if you can kind of think about it, you can dissect it into these steps. I think it makes it a lot easier. So remember, the whole goal here is we want to be able to, we're going to look at something interesting and dynamic. We want to look at the rate, we're going to compare the rates at which quantities are changing in some dynamic system, right? So we want to identify all of the snapshot values in the one frame in our movie, right? Because this is a moving picture here. This isn't just a single picture. This is a, this is a movie, right? It's dynamic, it's changing, but we're focusing on one instant in time corresponding to one frame. So we'll identify the snapshot values. We're going to engineer the calculus equation, we'll call it a differential equation soon, next semester. Where we want to be able to relate those rates by differentiating. So we'll start with the parent equation. If we ignore all the rates and we just start with the static quantities, we come up with whatever that static relationship is. Step 3 is we calculusify it, right? We're going to differentiate implicitly with respect to t, so we get the rates mixed in, and so it becomes a calculus equation instead. And then we just isolate whichever quantity is we're trying to find and plug and chug, right? So we looked at an example yesterday where we had gas being forced into a spherical balloon, right? And they gave us, so this is just a physical situation. The gas is being forced into the balloon at a rate of 400 cubic feet per minute, so it's coming out of some cylinder of compressed gas or something, and the valve is just open to a point where that's the rate at which gas is escaping, is entering into the balloon. And we want to know at what rate is the radius growing when the radius is 10 feet. So we've got this movie of this balloon expanding, and we're picking the one frame where the radius is 10 feet. So our snapshot starts with maybe r equals 10, right? What else do we know? Well, they gave us that the rate of change of volume, so v dot, what's the dot mean again? Derivative with respect to time, good. So that's dv dt is positive 400. And then we were looking for r dot. And so what did we do? Well, we first of all, we just ignored the dots. And if we ignore the dots, we've only got v's and r's involved in this equation, right? So the relationship between the static variables without the dots, it would just be the volume equation, right? Volume of a sphere is 4/3 pi r cubed. And then we can introduce the rate, so we can calculusify it if we just differentiate with respect to t. On the left side, we just get a v dot. On the right side, what do we get? So we had the 4/3 pi was our constant. The derivative of r cubed with respect to t, there's 2 layers to that, right? The derivative of hand cubed is 3 hand squared, and then the derivative of r with respect to t is my r dot. And so there's the differential equation that we want. We just need to solve for r dot, so we'll isolate that. If we isolate the r dot, this is what we get. So we solve that equation for r dot, and then we just plug and chug, and we got an answer. Okay. We didn't do this part though. Let's do this part. At what rate is the surface area growing when the radius is 10 feet? Okay. So we've already got this list of snapshot variables from part 1, and we have something else we could even introduce. Right now we know what r dot is. Right? We got an answer for r dot, so we could go back up here and 1 over pi in our units that we've adopted here, whatever our standard units are in this problem. 1 over pi is r dot. What is it that we're looking for in part B? S dot, right? Surface area. So if we call surface area capital S, then we want, there's our static equation, isn't it? We're looking for S dot for part 2. Okay. Okay, so we've already got, so step one is above, already took care of that. What's step two? We want to come up with the parent equation. Well, what's going to be the parent equation that's going to relate all this stuff? And really, we don't need the V anymore, do we? We're not interested in V in part two, so we could just cancel that one, right? But we know the radius is 10. We know R dot is 1 over pi, and we're looking for S dot. So doesn't that point us at that equation? Say it again.
How do you find R dot? What is R? What is S dot? What is this?
Well, R dot, that's the dr/dt, right? That's what we found. That's what this whole part A was about, was find the rate at which the radius is growing. Well, that's R dot, dr/dt, right? There's our R dot.
So we're looking at a balloon, and the volume is 4 over 3 pi over.
Well, that's just the volume equation for any sphere.
Yeah.
4/3 pi r cubed is just the volume of a sphere. Just from
Yeah, I know that.
yeah.
But like, what is the dV2 or whatever mean? I don't get it. I don't know what it is.
What that means?
Well, I get like, is that just?
That's that, right? The gas is being forced into the balloon at a rate of 400 cubic feet per minute, right? That's units of volume over time, right? So that's got to be a rate. That's a rate of change of volume. So that's what that means. That's what that derivative means. dV dt means the rate of change of volume with respect to time. That's one way. We haven't talked about it that way in a while, but we did, right? One way, all derivatives really just represent rates. In this case, it's a physical rate, right? How fast is volume changing with respect to time? Now, if we were to, here's another way to kind of think about this that might be helpful. I think everybody will benefit from this. So if we think about this, did I pull this thing up on Desmos yesterday? Oh, I did, right? I did.
No, I'm talking about yesterday. I was.
Monday.
I was here yesterday.
Monday. Yeah, Monday. So, on Monday,
Yesterday we had stuff.
yeah.
She was nice. I was awake.
So V of R just equals 4/3 pi.
What does R dot mean?
What's R dot? Yeah, dr dt. Instead we use dot instead of a prime.
Instead of like dy dt. Yeah. Like the dt always be on the block.
Yeah. Okay, so here's our function, right? Here's our function for volume as a function of time. Okay, something like that, okay? So notice that as R increases, volume starts to increase at a higher and higher rate as the radius increases. If I double the radius of a balloon, I'm not just doubling the volume, I'm increasing it by a factor of 8. So the volume keeps going up more and more quickly, right? But what's a derivative do? This is the v-axis. This is the v-axis, right? And this is the r-axis in this case, right? So as the balloon increases, you can see that, where did all that stuff come from? Right, you can see that as the balloon increases, this slope is changing. Now this one's measuring dV dr, but we could also be measuring dV dt if we want to, right? We could measure any rate we want to, but whenever we look at a derivative, what's that really saying? Well, the derivative is telling us, normally it's dy dx. In this case, it's dv dr. Right, so the slope of that line, that's what calculus does. It's telling us at that point right there, what's dV dr. Well, in our problem, we're not looking at dV dr so much. We're looking at dV dt. How fast is volume changing with respect to time? okay? And they're telling us the volume is changing with respect to time, that is how fast it's changing, that's a rate, okay? We could graph this if we wanted to. It's gonna look pretty boring, it's just gonna be a horizontal line at 400. The rate of change of volume is the same. Okay? What's the rate of change of radius gonna be though? Not the same. That's not gonna be linear. The radius is gonna go up in a way that's gonna be non-linear, right? It's gonna start off, and this is the deal with, like, remember talking about the balloon. The first puff of the balloon's pretty satisfying, it gets really big. After a while, you're putting in the same amount of volume in a puff, but you hardly notice any change, because the radius is changing very little after a while, okay? Does that help a little bit? I mean, at this point, I think the connection you need to make is any derivative is always a rate, right? When you're trying to identify what the quantities are, if you see units of volume divided by units of time, that's a rate. You're comparing volume to time, okay? Does that help?
And how did you find R dot?
We went through the whole process. We were looking for R dot. We knew the value of R, we knew the value of V dot. We know that we're going to start with this, we want to be able to make a comparison between V and R. Well, we have that equation. V equals 4/3 pi r cubed. But what we want to get out of that original non-calculus equation are the rates V dot and R dot. So I can set up an equation involving this R dot so I can solve for it. How do I get an R dot? I'm going to differentiate implicitly with respect to T, right? If I differentiate the left side of the equation, what's the derivative of V with respect to T? Well, just dV dt. That's V dot, right? That's what the dot means. On the right side, if I differentiate this expression that has an R in it, I know I'm going to get an R dot out of it, guaranteed, by the chain rule. When I differentiate the R cubed with respect to T, that's a chain rule problem. There's two layers to it. The first layer is the derivative of hand cubed is just 3 hand squared, right? But then I'm not done. Now I look inside the cube, the power function, and there's an R in there. The derivative of R with respect to T isn't 1, it's dr dt. So there's my R dot, the next link in the chain. Okay, now look, I've got an equation that's got an R dot in the equation. That's what I'm trying to solve for. So isolate it and plug the quantities in and see what you get. Okay? One thing you do have to be careful of though, and this, you guys wouldn't make this mistake, I don't think. It's pretty common with first year calculus students, is they want to plug in the values before they differentiate. Obviously that's a bad idea, right? If I plug in, for example, R equals 10, clear up here, when I differentiate the right side, I'm just going to be differentiating a number. What's the derivative of any number? Yeah, see, you see what I'm saying? You can't plug and chug until after you've done the calculus. Okay? So moving on down to part B, and just because I want to get through a couple examples. And if you have, I mean, come in and see me if you have questions, and we'll take this piece by piece, right? At what rate is this thing growing when, what is the surface area growing when S is 10? So we already have our snapshot values. What's our parent equation going to be, our static equation? Well, yeah, it's just the surface area equation this time. S equals 4 pi r squared, right? So step 2 is just going to look like that. Okay? This is a regular old geometry equation, but look what we did. We've related surface area and radius. So now, when we implicitly differentiate with respect to T, we're going to introduce those rates, which is what we're really trying to compare. What do we get when we implicitly differentiate with respect to T? So on the left side, what's the derivative of S with respect to T? S dot, right? Just ds dt, that's an easy one. On the right side, I've got this 4 pi that's a constant. So what's the derivative of r squared with respect to T going to be? It's 2 layers, right? Good. So I'm going to get the derivative of hand squared is 2 hand to the 1, right? Times the derivative of what's inside, which is my r dot. Okay? And so now all I've got to do if I want to solve for, well actually I'm just trying to solve for s dot. So it's easy to plug into. we've already isolated what we're trying to isolate. So step 4 is we just plug and chug. So this becomes, we could simplify this a little bit, I guess, right? So that's going to be 8 pi r dot. So 8 pi, the radius was 10, wasn't it? And r dot wasn't it 1 over pi?
Yeah.
So the pi's cancel, and I just get 80 is s dot. What should the units be? Now, we haven't,
Feet squared.
there you go, feet squared, right? Because we're measuring distances or lengths in feet, and this is an area, so it's got to be feet times feet. It's going to be feet squared, and then time is being measured in minutes. So it's going to be increasing at a rate of 80 square feet per minute. Okay? Okay? Got it? Okay, now let's try it. We started one yesterday. I guess I didn't see that bottom part. But let's go back to this one, right? Find the rate of change of the distance between the origin and a moving point on the graph of this parabola, y equals x squared plus 1. So this is, as you prepare for college, something that I think really helps with physics and math problems is, can you come up with some kind of a model that's just gonna, that's gonna help you understand this? That's why it's so helpful to take turns explaining stuff to each other. Because if you have to come up with an idea of a little bit of a model and kind of a way to articulate this, man, your brain, it just unlocks your brain and it just starts like a quantum leap forward. It just starts seeing things more clearly. So for example, one way that, like if I were, well, I am describing this to you guys, that's my job as a teacher, but this is kind of something that we started doing a lot in college, is we talk about problems like this, these parametric equation ones. Just think about them as wires, right? This is just a wire that determines the trajectory of that particle, or the path of the particle in the xy plane, right? So all we're trying to do, this bead is sliding along this wire, but it's sliding along the wire in this way. We're told that dx dt, the rate at which the x coordinate is changing, is a constant 2 centimeters per second, right? So we got to push that bead along the wire so that its distance from the y-axis is always increasing at the same rate, 2 centimeters per second. And we kind of touched on this a little bit at the end of the class Monday, I think. So in order for this thing to move along at a constant horizontal speed, after a while, it's really going to have to be booking vertically, isn't it? Right? To be able to make it far enough to the right every second. Everybody agree? So we should expect to see that as time increases, the rate of change of distance is going to get pretty big, right? Okay, so we want to know when, actually they don't even specify. Okay, well that's all right. So I might have messed this up, but this is still a good question. So our answer is probably going to be, it's not going to be a specific numerical answer, right? Because it seems like, to me at least initially, it seems like that the distance, the rate of change of distance is, it's going to change, right? What's the rate of change of distance? That's just speed, right? That's the speed of the bead in the xy plane. It's got to get going faster, right? So we'll just do the calculus and see what happens. So really the only snapshot value is that one. It's the only thing we're given. They don't specify anything about the x and y coordinates, do they? Right? Okay? So what is our parent graph? It's actually a pretty easy one.
Squared.
No?
The square root of x squared plus y squared.
You guys are making this way too hard.
Y equals x squared plus
Y equals x squared plus 1. There it is, right? That's the relationship between x and y, isn't it? Right? Okay, and maybe you're thinking ahead and you're thinking about even like distance or something, right? Okay, so I get that. Well, I'll accept that. So we could do, so we know that, okay, I see what Elton's saying. This is a good point. So what is distance? We'll call distance S. What is the distance in terms of x and y?
Square root of delta plus y plus x plus y squared.
Square root of x squared plus y squared, right? Agreed? Like if I take a point on this graph, there's my point, and this is what we started doing yesterday. Here's my point, x, y. And this, we called it S, yeah, I forgot we called it S, so we're on the right track. What is that distance? If it starts at 0, 0, isn't this just an equilateral triangle, right? So we've got this horizontal leg and this vertical leg. Well, that's just x, right? And that's just y, okay? So the relationship is S equals the square root of x squared plus y squared, but why make it so complicated? Why not just say S squared equals x squared plus y squared, right? Okay? So, right? Okay, if I need to solve that for S, I can just square root both sides. But if I do that first, if I square root both sides, I'm going to get S equals the square root of this sum. That starts to look like a pretty complicated chain rule problem, right? If I just differentiate implicitly here, it looks a little bit easier. So there's my parent equation. If I try to differentiate this right away, and we're going to go down a little bit of a dead end, and I want you to see this. We get 2s s dot, right, on the left side. On the right side, we'd get 2x x dot plus 2y y dot. Agreed? Okay, we could divide everything by 2, which would be helpful. We could just get rid of the 2's, divide everything by 2. Okay, but we've still got a fairly messy equation. Look at all the different species of variables we have here. We've got s's and s dots, x's and x dots, y's and y dots. Do I have information about all that stuff in my, up here?
No.
I do not, right? All I've got is information about x dot. So, how do I deal with that? What do you think, Kirk? Good, I could. So rather than have to go back and work in this step 1 and introduce a bunch of extra snapshot values, like calculate what y dot would be, that we can do it, but that's a little bit of work. Why not take advantage of the fact that we've got this built-in secondary equation, right? There's a way for us to eliminate a variable, right? We know what y is in terms of x, so let's just make that substitution before we ever even differentiate implicitly, right? In general, that's a great idea in calculus. We always want to reduce the number of independent variables as much as we possibly can before we dig into the calculus. And when we get into kind of the next big application for us, which is called optimization, which is even cooler than this, it becomes essential to do. Then it's really important then, right? So it's good, it's just good habit to start right now. So we'll make this substitution, and so we end up getting s squared equals x squared plus the quantity x squared plus 1 squared. Everybody see that? Okay, that's much better, isn't it? Because now I've got s as a function of x only, right? So we could simplify this before we do the calculus. It's worth doing. We'll just expand this out and collect like terms, and we can do that pretty quickly. S squared equals, so what is the quantity x squared plus 1 squared? It's like a plus b squared is what? Plus 2ab plus b squared, okay. So we're going to get an x squared plus an x squared is a 2x squared plus 2ab is, oh sorry, you're right, I messed that up, didn't I? This whole thing right here is going to become an x to the 4th plus 2x squared plus 1, isn't it? Now we can combine like terms and get what?
Where is it the 2x?
Because I've got 2 times x squared times 1.
X squared. Yeah, it should just be a 2x. Go down to the one that we were just working on. You've got 2x.
Oh,
squared.
yeah, I know why that's a 2. I think, did I not? I think I just didn't erase that. Should be that. Yep, there we go. Okay, right, x squared plus, this is what we get when we expand all that out. Now what do we get? So x to the 4th, how many x squareds do we get? 3, good. plus 1. So that's just a polynomial. That's easy. We like those. They're easy to differentiate, right? So now if I were to differentiate this, now we're going to get something better, right? We're going to get, if I differentiate, we're going to get 2s dot equals x to the, what do I get here? What's that term going to give me? 4x cubed x dot plus x dot plus, good. Okay, so what do I have to do on the right side then? Well, but factor out an x dot. Now notice, and you might be thinking that it's accidental that the x dot, it works out so conveniently. It's not. When you differentiate term by term, by the chain rule, you're always just going to get an x dot attached to every derivative, aren't you? Right? And so it's always going to work that way. It works out nicely. Yep.
Divide the whole thing by 2, real quick.
We can. Let's divide everything by 2. Okay, so that goes away, that becomes a 2, that becomes a 3. Good idea. We'll factor out an x dot, so we end up with s dot equals 2x cubed plus 6x times x dot.
Is that 3x? Yeah, 3x.
Oh, darn it, you're right. You gotta watch me like a hawk, don't you?
You just get so excited.
I do. Okay, and so if we were to solve this for s dot, which is our goal, let's just go up here. So s dot is equal to, I'll divide the whole thing by s. But what is s? Well, s is just the square root of that stuff, isn't it? Right? If I square root both sides. So I end up with a pretty complicated looking equation. Times x dot. Okay, so as we suspected, this is dependent on how far to the right we are, isn't it? The further we go to the right, probably the bigger this speed is going to be. Okay? So we can't really get a numerical answer to this. In order to get a numerical answer, we'd have to have a little bit of additional information about the question. Like maybe we'd have to say, if dx dt equals 2 meters per second, and let's specify x equals 10, right? Now we could know at that point how fast is the bead actually moving. Yep. Question?
We've got the x dot, how do we plug that in? Just so we have that.
Well, we can. Right? We can plug in the x dot. If we plug in the x dot, though, we still got x's stuck in here. Right?
And that's just an equation. Yeah.
Right. I mean, you could. Right. You could. Right. But more than likely on a related rates problem, I mean, they're going to give you everything you need so you can come up with a numerical rate. So let's just say x was 10. So when we're 10 to the right of the origin, and the bead is zooming along with a horizontal speed of 2 centimeters per second, what's the overall speed of the bead in the xy plane? We could find out. Plug in 10 for x and 2 for x dot and see what you get. Right? We don't have to go through the hassle, but we get a big number. Okay? Right? Okay? About one like this. We'll start it. Okay, so take a second, let's just kind of stare at that and read it for a second, and then we'll talk it over. Okay, what's the angle of elevation? Okay, but how do we always define, I mean, that's something you probably haven't heard of before. An angle of elevation is always defined as the angle between the horizontal and the object, right? So if you talk about an angle of elevation, like if we're looking at a mountain, you would just, if you were to shine a laser beam horizontally towards the mountain, it's exactly horizontal, and another laser beam up at the top of the mountain, the peak, then whatever the angle was in between those two is the angle of elevation, right? From your location looking at the mountain peak, okay? Okay, so we've got this space shuttle, it's being launched. We know that it's lifting off, and its height is given by this equation, S equals 50t squared, where S is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad, okay? We want to know what's the rate of change in the angle of elevation of the camera shown at 10 seconds after liftoff, okay? So, step one. Now, we're going to have to do a little work on step one. What are the snapshot values?
T equals 10 seconds.
That's the only one we're given directly, isn't it? Right. T equals 10. Okay, so at t equals 10, we know that this distance right here is s, right? And here's theta. Those are the variables, aren't they? Right, that we want to be able to connect. But we've got to be able to make t equals 10 turn into values of s and maybe even s dot. Okay? So s is given to us, it's given to us in terms of an equation. S is 50t squared, right? So if s is 50t squared, what is, at t equals 10, what is s? I'm going to write that down. S of t equals 50t squared. So our snapshot value at t equals 10, what is s equal to? Everybody agree? If I just plug in 10 for t, I get 50 times 10 squared is 5,000. So it's up almost a mile. Okay? Right? Can we get anything else? We can. We should be able to get, well, we can't get theta directly, but if they give us an equation for s, we should be able, that's the vertical distance, right? The vertical position. I should be able to find the vertical speed. What's the relationship between position and speed? Derivative, right? We know that velocity is the derivative of position. So v of t is just s dot, now we can call it, right? The derivative of s with respect to time, okay? Well, that's an easy derivative to take. What is the derivative of 50t squared with respect to t? 100 t, okay? So at our snapshot then, what is the value of s dot? No,
1,000.
because t is 10, right? And so if we look at that one frame in the movie, 100 times 10 gives me 1,000, and we're looking at what, feet and seconds, right? Okay, so now we've got this complete list of stuff that's given to us. What are we trying to find? No? Theta would be boring. Theta is a non-calculus question. Say it again.
Yeah,
We can. We can find theta. Yeah. No, we can't. If we want to, we can always go fill it in, right? We can always go back to row 1 to the snapshot values and add more stuff later if we want to or need to. We just may not need to. What are we trying to find? Theta dot. The rate of change. Find the rate of change of the angle of elevation. Well, the angle of elevation is theta. So really, this question is just about finding theta dot, isn't it? Okay. So look, we've got this triangle now. This is an important triangle, isn't it? So there's the relationship. This is S. This is just 2,000, right? That one, we wouldn't want to assign like a variable to that because it's just a number. It's not going to change. We need a variable there because that is changing with each frame in the movie, and this is theta. So using your SOHCAHTOA stuff then, can you come up with a parent equation that's going to relate S's and thetas?
That one that's on the board.
Oh, it's right there. You know, yeah, how about that? That one that's on the board. Okay, so yeah, we've got, so step 2 is just that guy, isn't it? And while we're at it, why not, I'll just leave it like that, that's fine. okay? So there's our parent equation, the static equation that relates thetas and s's, right? So now all we've got to do if we want to come up with our related rates equation is, well, actually, before I even say that, this t, do you get that this t was just kind of a, I mean, it really was, all it did was it just identified which frame in the movie we were looking at. You get that, right? Okay. So really that t was really only significant in that it allowed us to come up with those quantities, right? But now we want to be able to relate the rates of change of theta and the rates of change of s. So we got to differentiate implicitly with respect to t. So what am I going to get on the left side?
Secant squared theta, theta dot.
Okay, so I'm going to get the derivative of tangent hand is secant squared hand, right?
Yes.
Okay? Times the derivative of theta with respect to t is theta dot. Okay, and Kirk's probably already thinking, I told you, Mr. Roy, we needed that theta, right? Maybe you're thinking that. Because Kirk suggested we add theta to this. And you could. I'll show you a trickier way, though. You could do it that way. What about the other side? The derivative of 1/2000 s with respect to t, the 1/2000 we just leave out front. What's the derivative of s with respect to t? S dot, okay? So we're just going to get S dot over 2000, agreed? So we don't even really need the s, do we? Right? Turned out the s wasn't even important, which kind of makes sense. It doesn't really matter at what rate this thing is, how tall it is. All that matters is how fast is it increasing its height above the ground. Okay? The s does come into this implicitly. You'll see. So now we got to solve for theta dot. Okay? So we got a couple options. We could go back and solve for theta, and all we'd have to do is use Pythagorean theorem. Actually, we would just take a tangent of a specific value, right? We could say, solve the equation tangent theta equals, wasn't that 5,000? Yeah.
Yes.
5,000 over 2,000, which is the tangent of theta equals 5/2. So we could say theta equals the arctangent of 5/2 and just add that into step one, because that's a number, right? That works. We can do that.
Works out before.
Well, it works. If we solve for theta, I'm just going to have to divide each side through by secant squared, right? Agreed? So by dividing each side by secant squared, it's the same thing as multiplying by 1 over secant squared. What's the reciprocal of secant? Cosine. So isn't that the same thing as multiplying by cosine squared of theta? Right? So those guys cancel, and I end up with my equation being theta dot equals S dot cosine squared theta over 2,000. So we could use Kirk's method, which is perfectly fine. We could just plug in everything that we know now. We know S dot is 1,000, right? And we know theta is the arctangent of 5/2, which I could just plug in on a calculator. If I plug that into cosine and then square that answer, I'm going to get the right answer. Okay, there is another way to do this, though. If we go back to our triangle, let's call it a reference triangle. This is a right triangle. We could use the Pythagorean theorem to fill in the missing side, and if you do that, I don't think you guys did that very much in pre-calculus and trig, but this is a great way to handle these things. If I can fill in all three sides of any right triangle, then I can express any of the 6 trig functions as a ratio. I don't have to deal with any trig stuff, any angles, right? So if this is 2,000 and that's S, what's the length of the hypotenuse? The square root of 2,000 squared plus S squared, right? Okay. Oops, that's bad color. So there's the three sides of that. Cosine by SOHCAHTOA is the ratio of what? Adjacent over hypotenuse, okay? So we could then write this as S dot, which is 1,000, times, let's put this in orange. Multiplying by cosine squared theta is the same thing as multiplying by the ratio adjacent over hypotenuse, which is 2,000 divided by the square root of 2,000 plus s squared, and then I'm squaring that whole thing, right? Isn't that just cosine? Right? That's just number, well, actually, what's s? S was 5,000, okay? So this just boils down to whatever number this is. 1,000 over 2,000, which is just 1/2, times 2,000 over the square root of 2,000 plus 5,000 squared, if I just plug in s.
Isn't it 2,000 squared?
You mean that squared?
No, on the bottom, shouldn't it be the square root of 2,000?
Oh, you're right, 2,000 squared. You're right, 2,000 squared plus s squared. Good, thank you. Okay. And then that whole thing is squared. That's just something you plug in a calculator, right? Okay. It's just going to give us some numerical answer, right? And we never even had to actually solve for theta. I mean, you can. Either way, you got to use a calculator. You take your pick. You can solve for theta in terms of some calculator number, an arctangent, which you never write down, just leave it on your calculator. Or you can do this thing geometrically, right? You just don't have to do. You just don't have to do that. I do it this way. Like if I were doing it this way myself, I wouldn't have to explain to myself the whole process of how I get here. You can get to this pretty quickly if you just think about it in terms of, like you could have jumped right to the reference triangle. See what I'm saying? Okay. So somebody plug that in. What do we get? Got a calculator handy? Somebody? We'll just do it on Desmos. I want to know what the answer is. Do you think it's going to be a big answer or a small answer based on the context of the problem? It's going to be pretty small, right? If you're talking about the rate of change of an angle, that's not going to be very big. Shouldn't be.
Especially when it's that high off. I think it was probably larger line. Yeah.
Yeah, on the bottom, and then you
Yeah, I get that because, Jason, you took
So I get that that's, I mean, that's kind of a lot of stuff seemingly. But I want to remind you guys, you've been doing stuff like this all year where it starts off seeming like an awful lot of stuff and it ends up not being that big a deal. Oops. Yeah.
Are you going to be gone the next 2 days, or are we just kind of doing this?
Yeah, just more of this. And I got the recording thing fixed. So I'll record everything.